1/3 into the first quarter, so that kind of sucks for deadlines. So we'll go and get started with the ops track. I know yesterday we did like the recap thing. I don't know, do we want to do that? Do we just want to kind of kick it going for the sake of time, stay on schedule?
I think the schedule's pretty wide open. It's going to take an hour.
I can adjust accordingly. So.
Yeah, if you don't mind doing a quick recap, that'd be helpful. I mean, be you willing to do one? Because I wasn't here.
I mean,
at least on this side.
I wasn't here very much either.
Anyone want to do a recap for yesterday? Come on, be bold. All right, let's do as many as you can.
Okay. I know Moon actually did give me a presentation, but I don't have a dongle, and I don't want to deal with it. Oh. Yeah. Okay. So let me pull up the schedule. Look at the talks. I know I was really excited about the last talk, which was the MISP discussion, because that's something that I'm personally trying to kick off at work. And so it's nice to be able to see how other people are using it. So the first talk, here we go. The first talk was detecting DNS tunneling with Brad. I thought that was pretty good. I definitely saw some stuff there that I had never seen before. In particular, like the decimal encoded A records was, I thought, a pretty good obfuscation technique. JA3, I was really excited about JA3 as well. I had seen the ShmooCon talk, and I think good things are going to be coming out of that. I really liked his approach, like of taking an unusual way to solve a pretty difficult problem of like the Metasploit detection, not based on how he was doing it, and approaching it from a different angle, and then ultimately creating a very useful and multi-purpose application to solve that one problem. But you can solve a lot of other problems with it as well. Yeah, so as mentioned, one person actually was more or less like, hey, I want to set up something to do that. And so I don't know that there was a good solution that was like thought of, but hopefully someone runs with being able to create a little community there of like known fingerprints. I don't.
The reason why I ask is we should all pester them until they come up with some sort of community or a place where we can all share that as a community, because talk is cheap.
Yeah, I like action. And then we had hardened yet usable, reducing the effectiveness of common attacks. So that was kind of, taking the concept of a privileged access workstation and using when I thought about that, I was like, my recommendation has always been that our domain admins actually have a separate PC that's locked down, and they use that one PC for DOM admin type of activities. And so he took a very different approach to it, which makes the users a little bit more happy. And using that daily driver and being able to implement just enough security to make that an okay thing to do, which I thought was kind of interesting. 50 Shades of Grey log, I thought that was cool. I'm a big fan of open source stuff. Clearly, I forget that guy's name. He was as well. Eric? I think that's right. I'm a big fan of Elk. I'd never actually seen Greylog before, and so I was always a Kibana user. But it seemed simple enough to plug in. You could just point it at an existing Elasticsearch cluster, which I thought was pretty cool. Easy to implement that. You've got nothing to lose by giving it a try. Kimberly Pierce then with the down the open source rabbit hole. For me, that was a really interesting conversation because that's a problem that I've been struggling with at work as well. We've got 1,400 plus developers, and all of them want to install their own stuff right off the internet. And I'm like, what happens when you typo that package and you just installed a malicious one instead? And I liked her maturity model of being able to say, at least providing some tiers about being able to measure where you're at. And once you can measure where you're at, then you can start measuring it and identifying your gaps about how to move forward. So I really liked that one. Not even kind of in my wheelhouse, right? But I still liked it. Evolution of assessing one's security posture against offensive operations. So that was the talk that switched over to the philosophy track. I actually didn't attend that one. Did anyone else that can maybe speak to that?
Yeah, I thought it was a good talk. It was hard to see some of the slides because they were so small, but I think if nothing else, recognizing the resources available. So you can go to the MITRE website, you can look at the attack tool that they've developed, think about the kill chain, think about how you protect different scenarios. So it gives you a good framework to think about like where your gaps are. So if you're going to evaluate your defensive posture, you can use that in a red team, post-red team readout. Okay, we blocked all this stuff, but we don't have anything here, so it highlights those scenarios. So that was my thoughts.
So these guys were the ones that also built out the attack framework. If you're not already familiar with the attack framework, then you're about 2 years late. But it's only been like a year since people started really embracing it. So if you embraced it this year, you're still late. What is interesting about this is they're giving us a really early view into what's coming. And so they talked about the adversary emulation profiles, which give you a perspective of how various attackers actually navigate through an environment. And so these emulation profiles, they weren't sure if they were going to release it. They thought, well, who's going to want to use it? And lo and behold, they release it, and people think it's actually really interesting. So my suggestion on that is, instead of being 2 years late to the attack party, you can join the adversary emulation party much sooner and take a look at the work that they've been doing.
Then next talk that we had on the ops track was the Night of the Living Vulnerabilities, Forever Days in IoT, which I thought was pretty cool. I hung around for the first half of it before things got way over my head, but it was an interesting take around, the robot, which I never would have thought had such a dependency of, like, when it boots, it gets configs from FTP servers and being able to hijack that. And I kind of thought that was a self-contained thing, like a toaster, a robot, a toaster. It's the same thing. But it's not. That robot was super complex, and I didn't anticipate that. And then we wrapped up with that MISP conversation, which I thought was pretty cool. And when we talked about, one of the goals of the ops track was creating that action, like Sunil talked about. And so I was really excited to see the presenter be like, yeah, I'll give you guys, I got to sanitize some work documentation, but I'll give it to you. So I know I'm going to be pestering him about that. He's a year into that project, and I'm a month into it. So I'm hoping I can pester him enough that I can be a year into it in another month. So, and then for ops today, man, we've got some really good talks today. We're going to start off with Ian here talking about some fuzzing stuff. We got Brandon Dixon with one-click browser defense, a bro talk by Joe, and then that was close, doing science with near misses with Adam, and then preparing for a destructive malware attack. Then I know we've got at least one turbo talk as well, so if you have a quick turbo talk topic that you might want to do, hit me up on Slack, Zoom equipped on Slack, or come find me, and we can find you a slot for a turbo talk as well. Anything?
Okay, and then on the philosophy track, we really jumped into working groups to nail down put some meat around 3 different topic areas that we had discussed the day before. So the idea being, day one, we have a bunch of presenters talk philosophy, if you will, and ultimately provide some additional work that needs to be done, or provide a hook into additional work that needs to be done. And so there were 3 things that emerged from day one that we developed the working groups around for day 2. And those 3 working groups focused around how do we work towards professionalization of our practice. We walked through a number of different analogies of the medical community. What does that look like? I posed a very interesting question, which was, if security researchers do what they do in the medical field, then it would look a lot like human experimentation. And is that what we want? I think we all support security researchers, but we clearly need some boundaries, because otherwise human experimentation can go really bad, right? So the other framework was the product testing one. Joe Slowick and the MITRE guys led that one, and it was really around how do we frame an understanding of a more thorough look at how we evaluate security tools and their effectiveness, not just EDR products, but the whole suite of security capabilities. And then Kelly Shortridge led a discussion around, Kelly Shortridge and Jeff Briner discussed the hazard assessment framework. So Kelly had talked about doing hazard assessment and not not attack prediction. So instead of attack prediction, do hazard assessment, and we had some discussions around that as well. In the Slack channel on their philosophy track, you'll find the working docs that or the working group documents that we're noodling through. Today, we're going to continue to work on those documents, and if you want to see how we're progressing on those, you can hit the philosophy track. I'll pin them so that you guys can ensure that they're top of mind as well. We had two other Turbo talks. One was on an interesting look at deception in the context of the OODA loop, and how do we look at defensive weapons? What are defensive weapons? Not just defenses, but weapons that can be used in the process of doing defense. And then Steve Warren, that was from Guy Philippe. I forget his middle name. Anyway, got it. And then Steve Warren from Intel gave a talk on securing AI. So it's not, forget the buzzwords around AI itself. We know we're gonna see a lot of work around algorithms and artificial intelligence. What do we do to ensure that we don't end up building Skynet and getting ourselves all killed? So with that, I'll turn it back over to the ops track. Thank you very much. And philosophy track will start up in about 10 minutes over on the other side.
So with that, we'd like to introduce Ian, who's going to be talking about some fuzzing. Ian has asked that questions be reserved to the end, so when he's done, I'll kind of walk around with the mic if you have questions. Please give Ian a warm welcome. Thanks, guys.
All right, go ahead and get started. Everybody hear me all right? Okay. So I'm going to be talking about fuzzing today, at least fuzzing from a defensive context. A little bit about me before I start. My name is Ian Bridges. I'm a researcher at GRIM. We're like a cybersecurity consulting and research group. I specialize in VR, tool development, and usually mostly static dynamic analysis for products. Got my Twitter handle if you want to get information about the slides afterwards or anything like that, and ask about any questions of tools I'm going to talk about, that kind of thing. So why this talk? A lot of my work involves going out to or being contracted out to organizations to work on improving defensive postures, whether for systems or applications, that kind of thing. And usually on these kind of engagements, whether it be an actual application that has like source code and build process involved, or if it's actually like a internal system that is configured to run some service or expose some service to end users. One of the first things our group does is start working on fuzzers for whatever the system or product may be. We do that because the longer you run fuzzers, the more effective they are, and we usually gather up all the findings at the end, return that to our clients, that kind of thing, and offer remediation steps. But it's been extremely effective. I can think I've been doing this for 6 years now, and I think at the exception of one engagement, we've always found something when we use the fuzzers. And these aren't like internally developed things. These are off-the-shelf, free, open-source fuzzers. And it's usually kind of surprising when we bring this up and when we talk to clients at the end of the engagements, on the things we found, that kind of thing. And we asked a lot of times, well, have you ever considered implementing fuzzing as part of your development workflow, as part of your like defensive security posture? And the answer is usually no. And the reasons are usually things like, well, it's hardware, it's expensive to get a hardware range for fuzzing. Fuzzing, we never really considered it as like a defensive tool to use. And it's hard, there's like a high barrier to entry. So that's kind of what's prompted me to make this talk and submit it. Just kind of maybe clear up some of those misconceptions. And in doing so, talk about integration techniques, how you can add fuzzing to your existing workflows, and talk about two tools in particular that one is something that Grim's been developing and we're in the process of releasing open source, and something that I worked on just purely for this conference. So the overview of this talk itself, we're going to start with a little bit of philosophy stuff that has some operation stuff involved as well, just to kind of set the groundwork for the tools I'm going to talk about after that section. The topics I'm going to end up discussing are what I call the defender's advantage, integration techniques for leveraging that advantage, and then tools, the two tools I mentioned before. Over the course of this talk, I'm going to mention a bunch of different tools that can help with integrating, or the two tools themselves at the end. This talk is all focused on free and open source software. There's nothing wrong with paid services. They're actually becoming very popular for fuzzing as a service in the past 2 years. But budget constraints are a real thing, and focusing on, I think a lot of people would, like, I'm a big fan of the open source community, so focusing on those kind of tools that you can freely grab down and experiment with yourselves is something I really want to focus on. So before I start, I kind of want to point out a key distinction that's going to be important for us this talk, and this is dumb versus smart fuzzers. Everyone knows what a fuzzer is, but the distinction between the two can be a little fuzzy. Dumb fuzzers usually lack one or two key features, and it's knowledge of the target program structure, the thing that's being fuzzed, and knowledge of the target or knowledge of the target program's input model. So the kinds of input that the application or the systems are expecting from users. With dumb fuzzers, you don't really need that much information in either of these facets, because the way dumb fuzzers work, take AFL for example, is they basically take a set of inputs and then mutate them with a set of like mutators like bit flipping, splicing inputs and rearranging them, that kind of thing. There's no real knowledge going into the generation of or the mutation of the inputs that get fed to the target. And the target is instrumented in a particularly intelligent way. Most dumb fuzzers just use some sort of like basic block tracing to find edge cases or to detect new edges or crashes. So these dumb fuzzers can be, the efficacy of them decreases as program depth increases. So as your program is larger and more complex, your dumb fuzzers usually start, they're not as efficient as they were for simple and shallow applications. You usually compensate with that with throughput. So a good example is, familiar with Juru, who's a security researcher. He's at Project Zero, I think, right now. And a couple years ago, he released a blog post on some font fuzzing he did for Project Zero, and did so, found a bunch of critical RCEs accessible from like browser to get kernel mode access and execution. He released a bunch of those all at once, and it was the result of fuzzing Win32k.sys and ATMFD, which are like the Windows font subsystems. And he's able to do it with a particularly inefficient fuzzing system emulating the entire Windows operating system through box. And he was only able to accomplish the results he did because he had Google's hardware resources to throw it across. So he wrote it as like a distributed system and was able to do that and get the results because he had so much throughput. The focus of this talk is going to be on smart fuzzers because honestly, most organizations don't have the resources, the hardware ranges, or stuff like Google to do effective dumb fuzzing at a large scale. So smart fuzzers usually have one of those two aspects of knowledge about the target application. An example of some smart fuzzing is to use symbolic execution with something like CLE to generate test inputs that expand your code coverage. So CLE, if you have source code, you can instrument it, add some one-liners to your code, compile it through CLE, and then it'll basically output like an intermediate representation language, and then CLE will do symbolic analysis on that, find paths or find inputs that like branch deeper into your application. So your test cases are more than just randomly generating a bunch of like bit flips and that kind of thing. So you get better code coverage, slower execution because there's significant overhead, but a much more efficient reuse of resources. So that's why it's going to be focused on this talk is fuzzing smarter, at least from a defensive perspective, just because it is, again, most people don't have the resources to fuzz at scale with dumb fuzzing. Another problem with them is that they're typically highly specialized. These things usually come out of academic projects and things like graduate labs or we're seeing a lot more with participants in the DARPA's Cyber Grand Challenge. So they're usually built to work in like contrived scenarios. So it's kind of hard to apply to production code and systems. So on to what I've called for this talk, the defender's advantage. I found in my experience, fuzzing is actually a much more powerful tool if you're viewing it from a defensive context than when you're doing it as an offensive, like from an offensive context. And the reason why is because there's a source, I've kind of pointed out these key sources of advantages that defenders have over malicious third parties, and that is access and knowledge. So in the case of access, maybe you have access to source code that you can instrument or build in a certain way. Maybe if you're running a particular system, you have access to the system itself. A good example is kind of like front-end, back-end paradigm, where a malicious third party can fuzz inputs fed through a front end, but they don't have access to the back end. Let's assume it's properly firewalled off or something like that. Whereas when you're doing defensive fuzzing, you presumably have access to those back end servers in addition to the front end, so you can directly fuzz them as well. And you can instrument them in certain ways, like attach debuggers, you get access to crash dumps, you get access to logs, you can set up packet capture between the front end and the back end. These are all positions that third parties usually don't have unless there's some other like access point they can like pivot in or something like that. And then there's issues of knowledge. So a big like slowdown when you're trying to fuzz offensively is actually developing knowledge of the target you're fuzzing. You can always start your dumb fuzzer like AFL against and just hope for the best, but it's usually not an effective use of time. As developers or maintainers of system, you're usually the best people to know the system itself, know like where the access points are, the attack surface area, that kind of thing. So you can set up fuzzers accordingly to run in those particular cases. You usually have access to internal test cases as well, which can be used as like sources of inputs for fuzzing. So instead of rewriting all your test inputs, you just reuse the ones that you already have as part of like your unit testing framework or your regression testing, that kind of thing. Documentation is also a big one. If there's internal documentation for how a system's configured or how an application runs and the endpoints it exposes, setting up fuzzers based on that documentation is going to be a lot more efficient than the person who's acting as a third party and doesn't have access to that information, is just kind of poking around and hoping to find something that you can inject input into. So I'm going to go over some ways to like leverage that advantage. Try and get through these before as quick as possible to get to the actual tools and stuff. One of the bigger ones is deeper investigatory powers. This kind of goes back to what I was talking about when I mentioned having the front-end, back-end paradigm. Having access to those backends and being able to instrument those kind of services that might not be exposed to a user or a third party regularly gives you greater access to greater code coverage when you do your fuzzing. Again, attackers are limited to observing. A big one is side effects, observing those side effects. So the overall fuzzing process, there's the first part where you actually find an interesting bug or side effect. You have the second part where you actually try and triage that and weaponize it, that kind of thing. But if you don't have access to where the bug where the bug exists and where the side effects occurring, it's almost impossible to actually do that triage. The best you can hope for is like notice a denial of service on your end and say, oh well, that might have been me. As operating within a defensive context, you can do those things like attach debuggers, access to logs, crash dumps on the back end that you wouldn't have if you were fuzzing from an offensive position. Better input generation is another one. Again, you know your products better than anyone else. You know your input models more than anyone else. Better knowledge of that means you can generate better test cases, which means more code coverage, which means more effective fuzzing. Same thing with knowing underlying access points. You have access to knowledge that tells you that you can use to make decisions based on where to fuzz as opposed to as a third party, what is given to me to fuzz. Same thing, this is a thing that's come up multiple times in my experience, is that there's this issue with there's a misconception that you need like expensive hardware ranges to do this kind of fuzzing, and that's not true. Maybe if you're doing like large scale dumb fuzzing, you might want better hardware, but for the most part, most fuzzing ranges that I've seen have just been like decommissioned hosts. I think in fact like the like the most advanced, thorough one I've ever seen was just a bunch of, I think, T7500s that had been laying around in some back storage room, and they put a Pixie boot on them, and just manage them that way and have them running in the background. So you don't need particularly expensive hardware to do this kind of thing. You can also get creative with your implementation. I've seen in the past instances that have been effective where developer hosts were used as fuzzing platforms. So if you use something, you use some sort of distributed fuzzing management tool like FuzzFlow. I got the GitHub link down there. You can set it up so developer hosts, when they aren't being used, can be running fuzzing tests in the background. So after work hours when everyone's gone home, you can be using those boxes when they're not doing anything, their spare cycles, to run your fuzzing tests. And here's probably the biggest one, introducing fuzzing integration points into your products. Source code modification is probably the biggest example of this. For example, let's say you have an application and you've got a couple different inputs, or a couple of different fields in which users can input data, right? These are potential fuzzing access points. But you know that underlying all those access points all end up being fed down to the same similar function call stack. So with that knowledge, you can instrument your source code to add basically a fuzzing hook at that bottleneck in your application, and fuzz from that point down instead of trying to create 20 or 30 separate fuzzing test frameworks for all the different input fields that all end up getting bubbled down to the same bottleneck. So of course you wouldn't release this in a production system. This would be only for internal debug builds. But doing so allows you to fuzz faster and more efficiently because you're not bogged down in all the overhead of the external stuff, the high-level stuff. Yeah, and you go make sure you only expose these in internal debug builds. That was another thing I wanted to mention. Internal libraries as well is another fuzzing point that you'd have access to, or that you could develop, expose, whether you take you have debug DLLs that you can build, add your fuzzing points to the libraries themselves instead of the application to kind of get past some of the overhead. And I mentioned this earlier as well, reusing existing test automation. There's nothing particularly fancy about fuzzing inputs. So if you already have test inputs for your application, or like a workflow you follow for the system you administer, whether that be for unit testing or nightly testing or continuous integration testing, you can easily repurpose those test inputs to serve as seed inputs for your fuzzing system, whichever you end up deciding to go with. And the last tool is and a personal favorite of mine is one called Delta debugging. It's not, you can make an argument it's not strictly fuzzing related, but it follows kind of the same paradigm. And in Delta debugging, if you're not familiar with it, you basically take a known failure case and you effectively rethrow it over and over again while continuously attempting to shrink the input used to induce that failure case, with the goal of creating a minimal input or test case that creates the same side effect that you're interested in, but it removes all the overhead. So it ends up making it much easier to debug with that particular test case. It also serves as a great way to minimize your input corpus for fuzzing. So if you have a particularly large section of large collection of known crash cases that you want to include within your fuzzing framework, you can shrink those down, and they serve as more effective seeds because your fuzzer, you start mutating the bits that actually have consequences rather than just the overhead. And there's a GitHub link in there for a Delta debugging fork that Grudem manages along with, and if you go to that GitHub checkout, you also see a link back to the original version that we forked it off of. And finally, the last part of the philosophy side of things is provide a good example of this being instrumented and be done in the real world, and that's with Superlight. If you go to their website, their documentation, they've got a testing page where they describe their testing procedures. And in that, they talk about how they use fuzzing as part of their product test, or their release testing. And they use a three-headed approach using a custom-generated smart fuzzer that generates syntactically correct SQL statements. So instead of just randomly bit-flipping stuff and hoping for the best, they're actually generating SQL statements that pass initial validation checks and make it further into the actual application. They use AFL just because they have the resources to do so. So while it's not particularly good at finding deeper bugs, you still get a substantial number of test cases to cover a wide, shallow depth. And they also leverage their position as as a frequently used open source software solution to get access to Google's own hardware testing range. So even though they can't afford a hardware of their own, they can leverage Google's to do all the legwork for them. So that was kind of the philosophy part of the talk, basically going over why it's much easier to fuzz defensively than offensively, why you have a much greater advantage with doing so. You can write smarter fuzzers, and they're usually more effective as a defensive tool than as an offensive tool, and how you can integrate into some existing workflows. And I'm going to talk about two tools. The first is one that started as an internal research project at Grim called Killerkeys. We were having problems fuzzing on Windows particularly for client applications that were running on Windows. And the problem we ran into is that the fuzzing solution, the existing open source fuzzing solutions on Windows are usually limited in one way or the other. And it usually gets traced back to, in part, due to the what we call the fork problem, and that there's not like a native, efficient version of fork for Windows. There's Sigwin's implementation, but if you've ever looked at it, it's a nightmare, and it's slow. And Windows does have things like RTL, create process reflection, I think is the API call, but it's also slow. And that's a problem because most fuzzers work by, they get their throughput by using what they call fork servers to basically fork off processes at certain points instead of recreating the process over and over again to run for each new test case. So there are a couple popular Windows tool chains, and they usually have like ways to mitigate the fork problem. The two big ones are HongFuzz, which is a Google developed project, and WinAFL, which is also associated with Google. But they also have their limitations. HongFuzz, their big speed up, is based on compile time instrumentation, which is very difficult to get to work on Windows. And WinAFL uses a Dynamo Rio based feedback loop. So the way it works is that you instrument a target function, so you like provide an offset from the base of your application you're fuzzing, and an offset to a function. And Dynamo Rio, WinAFL will use Dynamo Rio to instrument that function so that once you hit the end of that function, instead of returning back to the caller, it ends up resetting your instruction pointer to the top of the function. So that's how you end up just looping through that function instead of creating a process every time you want to do another iteration of your testing. But that's problems when you're dealing with applications that have global state. So you're not resetting your context to a clean state every time like you are with fork. So you can run into issues there. So those are problems we ran into. From a defensive side, we ran into problems where we go on site for clients to work on defensive stuff, improving security postures, that kind of thing. And using like effective smart fuzzers was difficult and resource intensive because of like specifics about the tool, the products that we're there to help work on. There's usually some like small specific thing that needs like a custom. This application needs some sort of custom translation layer to get the inputs to it, that kind of thing. That made off-the-shelf tools just not particularly effective in one way or the other. So you'd have things like AFL that would work great for 90% of the application, but then some core issue meant you couldn't use it because AFL doesn't know how to pass inputs over like a protocol, that kind of thing. So that was kind of the reason why we want to start working on Killerkeys. So overall, what is it? Killerkeys is basically the glue that holds together a bunch of performant fuzzing components. So the way it works is you identify a component for integration. So let's say you have some code you wrote, an existing tool, that kind of thing. Let's say you have some way you have an application that you want to fuzz defensively. You know what the input model is, but there's no off-the-shelf way of getting inputs to your application. 90% of the rest of the fuzzing framework, something like AFL would work for you. There's just no way to get your inputs in with off-the-shelf AFL. So what we ended up coming up with was basically a translation layer, or an abstraction layer that lets you write your your product-specific stuff while reusing existing components from other performant fuzzing frameworks. So instead of rewriting everything from scratch for your particular use case, all you're doing is writing a component, or you're writing a component or two that's specific to your use case, and then you can reuse the general ones from existing products, open source software, that kind of thing. So the way it works is you write your component, and I'll talk more about those components later, integrate it into Killerkeys. The way you do that is through the Killerkeys API. That's kind of the secret sauce behind the whole thing. If it's like a custom thing you wrote, then you can modify the existing code base to adhere to the API, or you can write a translation layer that kind of does the conversion for you. But the general idea is that if you adhere to the API, your component's going to work with all the other fuzzing components, and you'll be able to build an overall framework just by putting in the specific stuff you need to work on your end instead of rewriting an entire thing. So once you do that, you want to test your integration, make sure everything's solid, and then you can start fuzzing. As far as fuzzing components themselves, Killerkeys has the concept of 5 core required fuzzing components. The first one is the execution component. It's basically, you can call it the driver. It's the thing that drives the thing you want to fuzz. So I think one of the first ones we looked at was Windows Media Player, so we needed some sort of code that would start up Windows Media Player, get to the right screen, and then feed it in an MP4 file or something. So that's the driver. It's also responsible for test termination detection. So with Windows Media Player, you have to know when your test is completed. So like when the video stops playing, when audio cues end, that kind of thing. So that's usually the extent of in most use cases we've come across. When doing this running against your own product internally, that's usually where all the code-specific stuff comes into. So you need something to basically drive the thing you want to fuzz and feed it the inputs in whatever format you need it to be fed. The mutation engine is usually reusable, but these are basically components that are responsible for actually creating your fuzzed inputs. A good example of that is Redamza. If you've ever used it, it's used by a bunch of different fuzzing frameworks, where you basically pass it an input or a grammar or something like that, and then it mutates it based on your parameters and gives it back to you, and then you feed it to whatever you want to test. These are usually reused, since there's a lot of good ones already open source on various code sharing sites. So there's usually not much work you have to do there. Instrumentation is also one that's usually reused. This is the thing that is responsible for instrumenting the application you want to test. So it's something like Dynamo Rio or Pin or Dynance, basically responsible for basic block tracing to do edge detection and for detecting interesting side effects. So memory corruption, crashes, user data being leaked, that kind of thing. Usually this is also just reused off-the-shelf stuff like Pin and Dynamo Rio. They're good products, and you don't really have to reinvent that wheel because it's a particularly complex wheel to reinvent. The tracer is also basically a branch of the instrumentation. This is also usually reused. It's like more thorough instrumentation, and the reason we have it is for it to basically run in the background and reduce your input corpus. So if your instrumentation process finds a bunch of interesting test files, because the instrumentation is pretty basic, it's just basic block tracing for the most part. Those various inputs might actually end up following like the same execution paths, or might end up being, at the end of the day, like identical to each other in terms of like actual code execution. So the additional instrumentation the tracer has makes that decision for you, and then it'll minimize your input corpus. So you're not repeating the same test case over and over again. And then some sort of generic record keeping tool. This is also usually reused. I think by default, we use the Postgres database for storing run results, jobs, targets, test inputs, seeds. The way inputs works, we store the seeds so that when the fuzzer pulls them off, you can regenerate the original inputs, so you're not storing entire data structure or input itself. So that's pretty generic, just basically storage. Killerkeys works in a distributed fashion using a modified version of FuzzFlow, so having that centralized record-keeping point is important. So here's basically putting all together. This image isn't like a workflow. It's more of a relational diagram. But if you did want to approach from a workflow perspective, everything kind of starts with a manager. Killerkeys is meant to work in a distributed manner, so that you can have, if you have some old decommissioned hardware, you can just set it up to pull jobs from the main instance. The manager basically has a hook in. It hooks into an optional input generator, so if you want to generate smart inputs using something like CLI, you have that option. Otherwise, you can just pull static inputs from the database. Manager passes that data to the host participating in the fuzzing job, who are running a main fuzzer. They take those inputs, pass it to the mutator. Mutator goes through and does its thing, mutates those based on what you've selected, feeds them back to the fuzzer passes them to the driver feeds those instruments, the target application you're trying to fuzz, passes those inputs to the application, and then waits the test termination, sends that back to the main fuzzer saying, hey, I'm ready for another job. All the test applications are instrumented via the instrumentation component, usually something like Dynamo, Rio, or Pin. In Java, the instrumentation component is just to determine whether an interesting test case has occurred. And you can define what interesting means to you, whether that's like a new edge has been detected, a crash has occurred, memory corruptions occurred, that kind of thing. Main fuzzer passes those interesting new seeds back to the database, which is pared down by the tracer, which is running that more thorough in the background, running that more thorough instrumentation. Also reutilizes the driver, because that code's already there to like get your input to where it needs to be, and basically be analogous to how it was originally found by the main fuzzer. So the tracer's running as a background process, and it's paring down your input corpus, just so you're not rethrowing or modifying what are effectively the same test cases. So that's kind of like the big picture overview of how all the components talk to each other and what they are. You'll see a couple things on here that I didn't mention, like the input generator. That's because it's an optional feature. It's not a required component. But if you do want to integrate smarter testing, that's how you do it, or smarter input generation, that's how you do it. Current features, we have drivers for Windows Media Player, Standard In, and the CyberGrand challenges, just for demonstrating what it can do and how it works. For the most part, drivers would be product specific. So if you have a product you want to test before release, you want to actually integrate fuzzing, like in some of the ways I mentioned earlier in the talk, then this is how you basically be responsible for writing the driver, since you know your product more than some random guys on the internet. And you probably have that invested interest in writing your own driver, not releasing it, if you do leverage some of those like fuzzing integration points I was talking about. Currently supported mutators, we have Redams. HongFuzz has a bunch of internal mutators that we've pulled in as well. Those work with Killerkeys, AFL as well, and some internally developed ones to demonstrate how that process works. Current instrumentation that's integrated is Dynamo Rio. I'm actually personally working on the pin integration and had some issues with pin tools itself, so I'm trying to work through those. Tracing is basically lifted from WinAFL with some minor modifications, and that just ends up reutilizing Dynamo Rio. And our current record keeping involves a Postgres database, but you can change that to however you want to store your own results. And uses FuzzFlow, like a heavily modified version of FuzzFlow, to actually do the distributed fuzzing node management. So going back to the Defender's Advantage I was talking about at the very beginning of the talk, examples of how you can utilize Killerkeys and your unique perspective, the advantages offered by fuzzing from a defensive context. And I mentioned CLE earlier, and this is kind of a great way how it integrates. CLE itself is an academic tool. It's usually not used with production code, and especially in like a fuzzing framework, just because CLE isn't a fuzzer, right? CLE is good at doing things like converting code to IR and then being able to do symbolic analysis on that, but you need to be able to use that symbolic analysis somehow. So with Killerkeys, instead of writing an entire fuzzing framework around CLE, you just have CLE let CLE do what CLE does best. In this case, do test case generation, which works off the shelf, and integrate it into Killerkeys, and that all CLE is responsible for doing is generating your test inputs, and then you can use all the other existing fuzzing components to for off-the-shelf stuff, and just let them take care of all the rest of it, as long as you adhere to the Killerkeys API. So that makes using something like CLE, which is powerful in like test case generation, makes it easier to integrate into your existing workflow, or use it however you want to use it to test your own products. So that's access, and as far as knowledge goes, again, this comes back to knowing your product better than anyone else, and writing system or product-specific mutators and drivers while reusing other performant components from fuzzing frameworks that are more generic. So I'm only responsible for writing the driver. I don't need to write a custom mutator or anything to work with that driver as long as I adhere to the API. I can just reuse other people's work who've actually invested much more time and resources into making performant mutators or performant tracing systems like PID tools. So instead of reinventing that wheel, you just reuse theirs. All right, so the second tool I want to talk about was, it's my own contribution that I worked on just for this conference itself. Since this is a working conference, and something I'm calling Git Fuzz, and the initial idea was to bring it to the conference and have like a working project people can help out on. Unfortunately, life gets in the way sometimes, so I had to put the project on the back burner. I plan on releasing it pretty shortly, pretty soon. But the product itself, the initial design goal was to create a tool that facilitates integrating fuzzing into existing workflows. And I was focusing on Git, just because that's what I'm familiar with, and how you can integrate fuzzing into things like nightly tests, or basically create a fuzzing equivalent to like nightly unit testing or like unit testing based on continuous integration principles. So those are the workflows I was targeting with Git Fuzz. And the way it works is it's basically a Git extension that allows you to run the Git Fuzz command in your Git checkout. You pass it basically a branch ID or some sort of branch identifier. Say, I want to run Git Fuzz on this branch. So if you got a development branch, that was kind of what I was envisioning when writing this. The way Git Fuzz basically works is that you clone out a Git Fuzz enabled repository or branch, and what that means is that there's basically a configuration file that tells Git Fuzz like what type of fuzz you want to run, and basically parameters of your fuzzing job, like what type of test inputs you want to use, that kind of thing. So that would be checked in as like a .ini or something like that. So Git Fuzz clones a repository, reads in that configuration file, builds the application. Right now, I think I currently support Make just like as a POC, and my plan is to work with things like Jenkins and or Hudson in the future. Build the application, locate the application's testing inputs, so like your seed inputs, and then start running the selected fuzzer based on your configuration against that branch, like after you've built the target. So the way I envision this working is similar to, for example, nightly testing, where you have workflows like you have a Jenkins or a Hudson job scheduled to run against your development branch at midnight. You pull down, build the code, and you run your unit testing against it. And so that when your unit test against it, so when you come in the next morning, you have your results of those unit tests available, so you can go back and see and get blame whoever you need to blame. So I wanted to mimic that kind of process, but with fuzzing instead of unit testing. So the same kind of thing, you schedule the Git Fuzz to run against a particular branch at a certain time. It runs, it pulls everything down, builds it, and then starts spinning up fuzzers against it. So instead of running your unit tests, you're running fuzzers overnight, and you get the results the next morning. Same thing with continuous integration testing, same kind of principle. You basically have Git Fuzz monitoring certain branches. So when code is pushed or pulled to that branch, you end up kicking off a similar set of tests, fuzzing tests on a particular hardware machine. So you end up immediately starting fuzzing based on like a push or pull basis, and you get results much faster. So the idea is to fuzz earlier and fuzz often so that you can get results back and identify potential issues prior to any sort of public release, and you get more confidence in your product. Version 1 I plan on releasing soon supported fuzzers, just AFL and QEMU mode. At some point, I'm going to support compile-based fuzzers as well, but that gets a little trickier with your build process. Currently only works with Make, just to demonstrate how the overall system works, but I want to add more stuff to that as well. And expects a fuzzing configuration file in your test, in the branch you want to test, and the test inputs to be accessible to the fuzzer. So with all the rest of that, Git Fuzz takes care of everything else, like setting up the fuzzing to run in a particular way, your output directories, all that stuff, and packages up the results and provides it to a licensed and readable fashion. All right. So as far as, again, going back to the Defender's Advantage I talked to earlier, I really wanted this to integrate to existing, make integrating fuzzing into existing testing workflows easier. So you can monitor development branches easier. You can reuse existing test cases. So if you already have unit testing frameworks, you can just take the tests you apply to those are the inputs you feed to those tests, and reuse them as seeds for your fuzzing, and to support distributed fuzzing across a development environment. So you're not responsible for buying that big fuzzing box. You can run it on developer hosts, that kind of thing, that you can distribute across maybe like less powerful hardware that you have just laying around you're not using. Okay, so I think I got through that with 10 minutes to spare. So this is my contact information. For Killerkeys, there's a GitHub link. We're in the process of releasing each component one by one publicly. And once we have everything publicly released, then we're going to switch over to public development. So far, we've released the API, and I know the mutators are getting in the final stage of our secondary code review. So it should be released soon. You can find updates on Grim Cyber. And if you want to get on, we have an internal mailing list as well. So if you want to get on that, or if you're interested in maybe getting some early access, just talk to me or hit me up on Twitter. Git Fuzz itself is at the final development stage. I was hoping to have it working for the conference, but I had to take some time off and deal with some stuff. But I have it like a working POC that I can demonstrate at some point later, and I'll probably post updates to that on Twitter, but I plan on releasing that shortly. So if that seems like it'd be useful to you, or if there's any particular features you're interested in, you can just talk to me and I can see what I can do. I think that is it, so I'm open for questions if anyone has them.
If there's like say a Maslow hierarchy of needs for like source code testing, where does this fit in as opposed to something like using a Fortify? If you're a defender, from a defender's aspect, like source code review and using tools like Fortify in conjunction with fuzzing, like where would you see this fitting in?
So definitely, like what you said, in conjunction. Basically, you run it in parallel. It's not a substitute for your existing testing processes. The reason why I like fuzzing, at least defensive fuzzing, besides the advantage you have over like a malicious third party, is that you can run it in the background. It's basically you start it and you just let it do its thing. You check in the results every once in a while. It's not like, say, static code audits or static analysis where you're constantly reviewing. Like there's like human intervention required throughout all the steps. You kind of just start it and let it do its thing, and you check on it every once in a while. Update your test cases, update the code you're testing, that kind of thing. But the actual legwork is being done automatically in the background. So start it early and just let it run and do its thing. That's the way I envision using it.
Any other questions? All right. Thank you, Ian.